Well, good day, everyone. Thank you, Julia. Thank you for the gracious introduction, and thank you to the C for having me today. What I would like to do today is I thought I would share ISHPI's experience in applying statistical techniques in the context of the software work that we do. And I looked at this from a number of different perspectives and thought about how I wanted to approach this. And I thought the best way would be to focus from an on-the-ground practitioner kind of perspective, focus from the perspective of software engineers and project teams and how we apply the techniques that we use in those contexts. Now, I'll be talking about some of these techniques. We do apply those techniques at other levels of the organization. At the overall organization level that the SEPG manages, our software engineering process group, to understand our organizational capability and to do a lot of analysis that way across projects and so forth and so on. But I think that there's this conception that things like metrics and data gathering and that kind of analysis is really the domain of the SEPG. And so I was really trying to focus on how our project team members and our project teams use these kinds of statistical techniques to provide value to the organization and to our customers. So what I thought I'd do first is set a little bit of context, and then the techniques that I'm going to focus on are, first of all, object size database, linear regression, prediction intervals, histograms, process performance models, control charts, and tests for statistical significance. I could have gone further, but I decided to kind of constrain myself there. I will be touching on a few other quantitative techniques that are not quite statistical in nature. I'll just touch on those very briefly, and maybe that's a topic for another presentation, maybe by someone else, not me. But then I'll kind of give some summary and perspective. And what I'll do before I go too much further is that just a few disclaimers. First of all, I do have a bachelor degree in computer science and mathematics, but I'm not a statistician. And to be perfectly honest, most of what I learned about statistics are from the SEI TSP team and from Watts Humphrey and from the personal software process and from implementing these practices in my organization. Probably statistics was not my strongest course at university. So I'll be upfront with you there. I'm also not a CMMI lead appraiser or a high maturity appraiser. And so, in fact, it's probably one of the few times that in this presentation, I'm going to mention the CMMI. My focus is really on what adds value for, for us doing software work. And then finally, like I said, I'm going to be trying to focus on practical application. And what that means is, I'm going to be showing some of our real data, and that means that not everything is perfect. And there are some things that, to the outsider or maybe even to the insiders, they raise questions, and I think those questions are a good thing. So my request to everyone is, be gentle. Thank you. So just very briefly about our organization, just to set context. ISHPI Information Technologies. First of all, it's pronounced ISHPI, ISHPI, and it's a Native American word that means to forward or to advance, high or high above. And we think of it as kind of associating ourselves to quality. We're a U.S. federal government prime contractor. I came from what used to be Advanced Information Services and got incorporated into our ISHPI AIS Division. And so, as Julia mentioned, we have our practices, which we term as high velocity development. And it's really emerging of practices that we developed over time and evolved over time, starting with the software CMM, the CMMI, the personal software process, the team software process, and other agile practices, and sort of melding them all together. And the data that I'll be showing today is focused on two sample projects that I think are representative of work that we do currently and work that we've done for a long time. One is a pretty small project. It's a 2-person software sustainment application web application, sustainment of a web application. Another one's a larger project. It's a 10-person software sustainment project with a large information assurance component. And there's a suite of about 20 different applications that we support as part of that that effort. So the data that I'll be showing kind of comes from that perspective. So again, finally, last slide, kind of talking about context. I want to talk about data collection because this whole presentation is premised on the fact that, you know, we're doing statistics on data. And so what that means is that the data has to come from somewhere. And so where does it come from? And ultimately, all data comes from individuals. And it flows up to teams, and then those teams submit data to the organization, and then teams use aggregated data, either their own historical data, and in some cases data from the organization to help plan, and vice versa. Individuals use data from the team in order to do their work. So the data flows in both directions, and that's really, really critical, that data flow. But ultimately, that individual data collection is just really, really critical. And then in terms of the data collection framework, obviously the general life cycle that happens at a lot of different levels of abstraction is that either as an individual or as a team, for an increment or perhaps for a full project, that team does estimation and they create plans, and then they use those plans to execute their work. And during that execution, they do that data collection. Again, at the individual team level, they flow it up to the individual level, they flow it up to the team level. The individuals and teams use that data in as they go through their work. And then at various points in time, they do retrospectives. And those retrospectives do two things. There's the traditional perspective of, you know, what can we learn from this thing that we just did or that I just did? So what went well, what didn't go so well, what can we do differently in the future? But the other key thing about retrospectives for us is it's really a chance to collect data, to vet that data, and to, you know, perhaps clean it up, make sure it's correct, complete, clean up any discrepancies, and to do some analysis on that data to understand what we can learn quantitatively. And perhaps statistically. So I think those are all good concepts, and those things, you know, kind of happen again at the individual level, they happen at the team level, and they happen occasionally at the organizational level as well. So in our organization, and maybe all organizations, all of our metrics, our analyses are really dependent on just 4 fundamental measures, and those are size. One of the size measures that we use most are lines of code, but not exclusively. And sometimes where you might think we might use lines of code, we don't always. We use effort always, and that we track to a resolution of about tenths of an hour. Everyone tracks their time to the 10th of an hour. So that has a couple of advantages of everything just goes to 1 decimal place. So that's kind of nice. Then schedule, which means task closure. When did things finish? When did they think that they were going to finish, and when did they actually finish? So are we on schedule or behind schedule? And then defects. And what I mean by defects is, you know, was something wrong that had to be redone in order to be the right way as it was expected to be. So as I mentioned, all of this data collection and activity really depends on individual team members. So there's the saying here in the US, all politics is local. Well, for us, all data is local. So it really depends on individuals being trained and having some standards or guidelines, and really a culture and some expectations set about how everyone is to conduct themselves in terms of data. And part of that has to do with, you know, the notion that data is there for the good of the community and isn't used against anyone. And then finally, the tools that we use. We don't use super high-tech tools, Excel, obviously. We use a statistics plugin for Excel called SPC for Excel, and there's a web link there. For counting lines of code, we use Beyond Compare is a nice, convenient way of doing that. And then we have a series of internal tools that we've used over time that help us with time tracking and our various repositories and task tracking and quality tracking and projections and so forth and so on. So the first of the concepts, okay, first of all, an object or component size database. So this is a technique that we reference at estimation time in order to be able to choose what are often called t-shirt sizes, your very small, small, medium, large, very large, relative sizes of different pieces of work that we might be planning on doing. And I know in some of Brad Hodgins's talks, he's talking about, how big are the rocks in the pile. So this is really that kind of an exercise. So we populate that database, as I mentioned, in conjunction with retrospectives that we perform. And what that does is it captures actual, and I put in quotes, sizes, actual sizes of components that we've developed in the past. And we do use traditional sizes, that is lines of code for coding components or, for other kinds of work products. We most commonly use, for example, like pages of documentation that we might need to be producing or other kinds of things. But not everything necessarily correlates really strongly from size to effort. And one of the main things that we want to do is we want to choose these sizes to help us to predict effort. So when that doesn't happen, we use effort directly. And so we do use sizes, especially for new development. It's very important for us. But for sustainment kinds of effort, we have used new and changed lines of code and lots of variations on that theme. But for us, oftentimes we just end up reverting to effort directly. We also do sometimes create subgroups for different types of work with different distributions. So for example, UI work might have a different size distribution in terms of the smallness or very largeness of components compared to database work or middle tier work or other kinds of work. So we oftentimes aggregate those into their different piles. So this is how this works. I should point out, I was going to make a point to myself here. We happen to not use story points. I think story points are just fine. I don't have anything fundamentally against them. For us, what makes sense to us is to be as objective, as empirical, and as measured as possible. And so for us, we like being able to just measure the actual physical output of what we've actually produced, but where that makes sense. And again, that doesn't always make sense, and that's fine too. For Scrum, I know Scrum teams often conduct themselves. They use planning poker, and they often use a Fibonacci sequence or similar. So this is maybe an alternate way of looking at that same concept. So here we have some actual data of that I've sanitized a little bit. This is 103 components from one of our teams, and these are actual hours in this case. The number of hours from the different components that have been produced over time. And the thing of it is the way that sizes of things, whether you're talking about lines of code or whether you're looking at effort, they tend to bunch up in kind of a non-normal distribution that's skewed heavily toward the smallish end. And so what we want to do is we apply a little algorithm to help correct for that to get sensible size ranges. And so what we do is we take just a natural log of each of those. Excel does that very easily. We take the mean of those and the standard deviation of those, and the mean ends up being the medium size of the component. And so a medium component would be that in its log form, and then we take the anti-log of each. And so in this case, A medium component would be 28.4 hours. And then small and large and very small and very large would be plus or minus 1 or plus or minus 2 standard deviations from that. So we take the that 0.625 and apply that to the 3.345 and get those numbers and take the antilog of each. So very smalls end up being 8 hours and very large end up being 99 hours with 28.4 hours in the middle. And this gives us some size ranges that are pretty sensible for the developers who need to estimate future components, and it gives a guide. And it gives a guide that flexes with the sizes of the actual components that they've built. So what that means is when they go to build to estimate a new thing, they say, well, this thing is kind of like that other thing, and that other thing was of this size, so therefore, it's kind of like that one was medium, so we'll choose 28.4, and that's the size of the rock in the pile that we'll estimate. So just to illustrate this notion of how this distribution works, when I plotted those actual 103 components, this is how they're shown. The most common components are down here, around 20 hours or, maybe even 10-ish hours, and a lot less are, 40, 60, 80, 100, 120 hours. So just taking the averages and plus minus standard deviation doesn't work as well. If you take the log of each of those, you get something that looks a lot more like a normal distribution, that it makes sense to do plus and minus 1 standard deviation, plus and minus 2 standard deviation. So these are actual components that are in our database that's in one of our projects that our team members use to understand the sizes of the components that they've built in the past and use that to estimate the sizes of future components in the future. So next technique that we use is linear regression. Of course, I think most of you would be very familiar here. It's an analysis tool just to help understand correlation between two data sets, and there's lots and lots of different uses, of course. It gives a best fit regression line through that data. So many of you know from secondary school algebra, the formula y equals mx plus b, that's simply the formula for a line. So here the multiplier is called beta 1 and the constant is called beta 0. And we reference this at estimation time to correct for estimation bias that we all may have. And we do this sometimes at the individual level. We do this at the team level sometimes when we're planning activities that are not necessarily coding components. And sometimes we do this for whole projects, and I'll talk a little bit about how that works. Again, we update this data in conjunction with retrospective. So here we have the historical data, and again, this is around 100 and some odd components that have been built. Along the x-axis is how many hours we estimated using those relative size ranges, and then on the y-axis is how many hours those components actually took to build. And there's a strong relationship there. It's not a super great relationship. The multiplier there is 0.95, so it shows that on average we kind of very, very slightly tend to overestimate. And I have a feeling that this is probably due to some bias because of that's kind of what our customer would rather us be conservative in our estimates and sort of undercommit and over-deliver. So that's just kind of the culture on that project. So I think that's maybe why that could explain part of why there's a slight tendency to overestimate. And so the multiplier there is 0.95. So on average, it'll reduce an estimate by about 5% and then add a constant of about 5 hours. The R-squared value, which is the correlation coefficient, indicates 0.6. A 1.0 would be a perfect correlation. So this is not that. Anything above 0.5 is reasonable for planning. Anything above 0.7 would really be preferred in terms of giving a nice strong correlation. And something in the 0.8 to 0.9 range would be ideal, but that's not what we have for these components. And of course there are some cautions here. This is a relationship that makes sense, but every once in a while you get a regression chart that kind of looks like a shotgun blast, where there's no clear, obvious way to draw the line through a set of data points. They could go on a nice, proportional slope like this, or they could be vertical or horizontal or even backwards. And so sometimes you have to be careful not to blindly apply a regression line that just doesn't make sense. The bigger we think it is, the smaller it actually turned out to be, is probably not the approach we want to be using. And then the other thing is to choose historical data that's similar to the future work that's being estimated, of course. And so the components that we're choosing, after projects get going for a while, they most typically use their own data versus organizational data as the basis. So next, I'll extend the concept of linear regression to prediction intervals. And so in this case, we apply, it's the analysis that we do from linear regression, but then we apply an extra step to it. So here we have our historical data. And given the historical data set of our X values, that's all the estimates that we've done. Each of those has an actual value of what it actually turned out to be. So those are each of the blue dots. And so then given a new estimate, the question is, what would my new most likely adjusted estimate be? So for a new XK, like 150, what would that actually turn out to be? We apply a regression formula and it would turn out to be about 140-ish or something like that. But then the question becomes, what our prediction interval says is that based on some confidence interval, like say 70%, what would be the expected range around that most likely estimate? And so we have what's called an upper prediction interval and a lower prediction interval, and that's based on the statistical distribution of the historical data. So the tighter together those data points are, and the more closely they line up on the regression line, the less range the upper prediction interval and the lower prediction interval will be. And so how that works is that based on that XK of say 150 estimate, then the YK, like I said, might be 140, but plus or minus some range. And so, what we could expect is 70% of the data points would fall between almost 200 hours and maybe as low as 100 hours. And so that's the range. And so when we're making commitments, we can think about risk and the amount of risk that we're willing to absorb. So here, this is some activity level. So these are not individual components, but it's a little broader, larger in nature in terms of activity level things that are not necessarily coding components. And so that has a distribution that looks like this. And what that means is that 70% of the data points would fall between these bounded lines. So if I estimate 250 hours, that's going to be plus or minus the lower upper production interval. And so it could be as high as 275 and perhaps as low as 180 or something like that. And so that helps us to understand what level of commitment we want to make. Now, it's worth pointing out here that when we choose, maybe we don't want to use the raw estimate of 150 because we want to correct for our bias. So 150 would then go to 140. But for many projects, it may actually increase somewhat. But if we want to hedge ourselves against risk, we could choose to estimate instead of at that corrected estimate, we might basically build in that padding, if you will, which is a responsible thing to do because it shows that we do have data points that land in that range. But what that means is, although 70% of the data points would fall between those bounding lines, 85% of the data points actually fall below. So when we choose a 70% prediction interval, you also get that 15% on the lower tail, which means 85% would be down here and only 15% of the data points would come above. So this brings me to a question that our team was asking themselves when they were estimating using this data set. So we had this historical data and we needed to estimate a whole bunch of activities going forward. And the question is, are the new activities that we're estimating a lot like the ones that we have historical data about? So the team decided to use histograms to understand that. So of course, histograms are an analysis tool that you can use to sort of understand or visualize the distribution of a data set. And it helps to spot similarity or differences in the distribution across multiple data sets. And oftentimes we will use this as like a before versus after, or in this case, the before is the historical data and the after is the actual future hypothetical estimates that we're putting together. So the question is, we had these raw estimates and this is the way the size of things were distributed. And so the question is, if we're going to apply this regression and we're going to apply upper prediction intervals, are we estimating new things that are sufficiently like the things that we have data about, or is the distribution completely different? And oftentimes when we apply a regression or an upper prediction interval, the impact that it has on larger components is much different than the impact that it has on smaller components. And so it could have, if the distribution is different, it could really skew the commitment that we're making. And so we did this distribution and we looked at the two, and you can see that the shapes are nearly identical. So that was helpful for us in terms of just having a level of confidence that, yes, this historical data is useful for the new data that we're estimating. This is also helpful in conjunctions for with tests for statistical significance that I'll talk about here in a few slides. And then process performance models. Now, this is a little bit of an oddball because it's not really a statistical technique in and of itself in the way that control charts or histograms or other regression or prediction intervals are. But it's really a way of applying some of those things together in order to model a situation. And so the idea here, and by the way, this is a CMMI term, it's used throughout the model. And the idea here is to start with some kind of a standard stable process that you understand. And what I mean that we understand, we understand the process capability and we understand the variation around that. And so we use that historical data to provide some new process inputs. And so, for example, the estimation process is one that we have refined and we understand the process capability. And so we use those new process inputs against that stable standardized data set to predict some likely range of process results from those inputs. But then what we can do is we can change some control parameters to play some what if games. We can change some things to do some hypothetical scenarios to see if we change X or we change Y based on our process model, how might that statistically change the range of process outputs? So what does that look like? Well, what it looks like for us, one of our main process performance models is exactly what we just talked about. The regression model forms our historical process performance data. And of course, we have our new inputs, which are our new estimates. And so we're applying our regression line, our y equals mx plus b to those. And we apply our upper and lower prediction intervals to understand the range of possible outcomes for each of those estimates. And so then what we can do is we can say, well, what happens if we want to be more risk averse and instead of a 70% prediction interval, if we want to choose an 80% prediction interval? So instead of choosing like an upper prediction interval that would cover 85% of the data points, an 80% prediction interval would cover this 80% in the middle plus an extra 10% on the tail. So we'd kind of be 90% confident about giving an estimate at the upper prediction interval. Or what happens if we want to be, if we can absorb more risk, or we feel that we can if something changes or something goes wrong, we can transfer more of that to the customer and renegotiate. So maybe we can go with a lower than 70% confidence interval. So this is a way that we can help to manage risk and to play some what if games along those lines. And so that's what our process performance model is doing for us. And again, we use this at estimation time, not so much at the individual level, but we do definitely do this at the team or activity level when we're estimating for different increments that we may be committing to. Or sometimes we're doing this at the project level where these data points are very large data points, thousands, tens of thousands of hours to bid a whole contract. And we have historical data on, well, when we've bid a contract at this level, we know that it's performed within this range. So therefore, how much risk do we want to absorb for a fixed firm price bid, or maybe a time and materials bid, or things of that nature. Now, it's worth saying here that there are some other quantitative models that we do apply that those are well described by the team software process, things like earned value projection, our schedule projection model, and our quality projection models. Those don't quite meet the criteria, at least for CMMI 2.0, of what they would consider as a process performance model, because it's not a full statistical model. So in order to take it to that next degree, you may have to do something like a Monte Carlo simulation or something like that in order to add in some additional statistical nature to those projections. So although they are definitely quantitative performance models, they don't fully qualify as a CMMI process performance model. But this one is a good example of one that does. And I think it's very useful. And then control charts. Of course, I think many on the call, on the presentation today attending would be familiar with control charts, but the idea here is to understand whether a process is under control. That is, does it behave in a natural or relatively predictable way? And in fact, the boundaries that are drawn when generating a control chart are called upper control limits. They're the natural limits, the upper natural limit and the lower natural limit of how you would expect that process to behave. And so the idea here is to understand the process capability. In other words, not just on average what happens, but also the range of outcomes, the amount of variation that is happening with within our data over time. And so we look at these sequentially as each data point is gathered, as each component is built, as each peer review happens, or so forth and so on. And then we understand that over time, and we monitor it to understand, is it under control? Some key processes that we do apply control charts to at the team level are our estimation process. So this is an example of an actual team's estimation percent deviation. So here at some point we were averaging about 22% effort deviation for our estimated components. And then we did some causal analysis at some point, and that fell to about a 10% average. But just as importantly, the range around that average changed and it tightened up. And so we had less variation or less deviation from the mean, which is a good thing. The other thing that happened is, for the first little while when those data points were being gathered, all those data points were under control. But then over time, you can see what's happening here is that very slowly, but very surely, that mean is really starting to creep up. And so what's happening is these early data points are no longer shown as being under control because they fail some of the under control tests. For example, too many data points in a row on one side of the mean, or within a certain range, zone A, zone B, zone C, et cetera. And so it's really time for us to think about, hey, has something changed? Do we have to redirect the team back to understanding, why this is happening? Do we have to take corrective action in order to get the process back fully under control? So those are all things to be watching out for. It's also worthwhile noting that we also track control charts for system test execution, defect density, and acceptance test execution. But to be honest, those control charts look pretty awful right now. And the reason is that we have so many data points that have zero defect, which means they have zero defect density, which means, you can't have negative defect or negative defect density. So basically all the zero data points are on the same side of the mean, and any defect that happens is on the other side of the mean. And so then you get all these out of control data points. So from an under control standpoint, that's something that we're looking at, how to look at some alternate ways of dealing with that. So I'm not showing those data points, but it's worth, maybe we're kind of treating that more as a run chart than a control chart. But I did mention that peer reviews are one of our most critical quality steps. And so whether they're design peer reviews or code peer reviews. And so here we have a control chart that's divided into different regions and the mean and the variation around that. And this is showing that the prep rate, in other words, the lines of code per hour that are spent, how fast the inspectors are reviewing the work product is shown as being under control. This is very stable. And what we did was we segregated those data points by major changes in the team's composition. And so this is the small team, and so it is sensitive to team member changes. And so we want to make sure that it's under control. And then the defect density, and what it shows here is there's a different behavior than what we would expect to see. There's a lot of data points, zero defect density, that is zero defects found in peer review in a row, or very few. And so I guess a point to make here is that that's not necessarily a bad thing, but it is something to be looked at. So, a couple points here about control charts. Typically, 15 to 20 data points are required to be considered a valid control chart. So for example, this left edge of the chart here, when we had one team composition before it switched to a different one, this one has to be treated with a high degree of, take it with a grain of salt, but it's useful for visualization purposes. All the rest of them pretty much have about 15 data points. So those are considered valid. 20 is better. And then I've shown here the out of control test. I won't go through them. They're well understood, through Google, Wikipedia, or through SPC for Excel has some good material. But the idea is that the out of control tests indicate that somehow the process is behaving differently than what you might expect if it was just sort of naturally going along. And so what's happening is there's a signal. Now, is that signal good, or is that signal bad, or is that signal indifferent? That's up to you to decide, but just that the circumstances should be investigated. And what I can say is that, for example, these data points that, for example, over here, where we had some outliers that were like right at the 3 sigma range, right at the upper natural limit and so forth, those did have causal analysis. We could think about maybe whether to remove those, but the fact of the matter is that those kinds of data points do occasionally happen. So, we look for special causes, but we also need to look for common causes as well. And then the final technique that I'll just touch on is test for statistical significance. And the idea here is that in the case where we decide that we're going to make some kind of deliberate process improvement, the question that we would ask ourselves is, did that change actually have the intended desired effect that we wanted to happen? And when I say, did it have the intended effect, quantitatively speaking, did it have the desired effect? And so then the opposite question that we could ask is, is there a chance that these improved results could have happened by accident or just as a matter of by chance? And so that's one scenario, but another scenario is that we might notice over time that, hey, this process seems to be behaving different than we're used to it seeing. Is that kind of normal, or might that have happened by chance, or is there some specific change that maybe we're aware of or maybe not, that we may need to look into. So there's a statistical technique called a t-test for statistical significance. And again, I'm not a statistician, but the idea is that, like in this case, we have been monitoring the time spent in ongoing effort as opposed to on-task effort for earned value tasks. These are sort of ongoing types of management things. They could be team status meetings or technical meetings that are not specific to any given component and things like of that kind. So there's some specific types of ongoing effort that we noticed we were monitoring and there was going along, and then there was a team change, and then we seemed to be seeing some data points that were different than we were used to seeing. And so the question is, is this happening by accident or is this happening not by chance? And so the null hypothesis would say, well, assume this is happening by chance. And so then we apply a pretty straightforward statistical formula. Excel does it very well. It'll calculate a p-value based on the student's t-distribution and calculate that p-value. And the idea is if that p-value is less than 5%, 0.05, what it means is that there's a low probability, a very low probability that the null hypothesis is true, and you can reject that null hypothesis. And so in this case, what it tells us, this is a very, very low p-value, so there's a very low chance that this happened by chance. There was some specific change that happened or a set of changes that happened to give this different, very different behavior. This is a very different distribution, a very different mean than what we were used to seeing before. This is sensitive to numbers of data points and also the changes in the distribution and where the mean is. So definitely something happened. And so in this case, we dug into that and we realized, aha, there's some training that really should be happening. So there's some additional training that we did, some additional mentoring that we did, and in fact, some additional understanding that we conveyed about the time tracking practices and what should be considered that kind of ongoing effort versus tracked elsewhere. And after we did that, we kept tracking for a while and we got these data points. And so what's pretty obvious even visually without running a t-test is that these data points are very different than these data points. And then after we did our change, those are very different than these. And so it's very clear that that didn't just happen by chance. But then the question became, well, are these data points over here distinguishable from those data points? So we ran a t-test against those two data sets and we got a p-value of 0.47, which basically means that, yeah, they're not very distinguishable at all, that it's really essentially the same population. So that's a good thing. It kind of brings us back to where we thought we ought to be. So those are the items that I thought I wanted to discuss today in our presentation. The perspective that I want to bring here is that all of these techniques are placed in a context where they're really providing business value for us. This is focused on the capability to make responsible commitments. It is around, for example, our estimation process, the ability to commit effort, schedule, cost, and you can see where those have a lot of business value. And also our capability to manage quality, things like our quality practices, especially our peer review practices, but also monitoring our system test defect density or acceptance test defect density as well. And so all of those contribute, and in fact, quality and having quality under control is a key factor for us making responsible commitments and being able to meet those commitments because, of course, poor quality and rework is inherently unpredictable for us. And so all of this kind of combines together to enable our customers to have a positive experience, consistently meeting our commitments and consistently delivering first time right. In terms of our statistical techniques, they really, I feel, provide a deep understanding of our capabilities of what we can do. And so for us, data is something that we live by. Data is awesome. And so my gentle suggestion to everyone who maybe on the presentation today attending is to, start out gathering data and be consistent. Consistency, having some operational definitions and consistency across, individuals and team members is important. And then use that data, whether it's at the individual level, at the team level, at the organization, use that data, analyze it, learn from it, and then use that to continuously improve and apply that back to the feedback loop. So I hope that this presentation has given you some ideas of maybe you don't have the same circumstances in your organization, but maybe there's a few nuggets that have given you some ideas, and I think that's just great. That's what I was hoping to accomplish. So I was hoping that you might have some idea of how you might be able to apply these kinds of statistical techniques in ways that help your teams. I want to thank the Software Excellence Alliance for having me here today, for inviting me to do this presentation. Of course, my thanks to Watts Humphrey and the whole team at the Software Engineering Institute, the TSP team. I've learned so much from all of you over the years. And of course, all my team members at the ISHPI AIS Division, especially my colleague, Barty Perenni, the Director of Software Process Improvement, and then Gir Seshagiri, who hired me many, many years ago, and grateful for everything that he's taught me and all of his mentorship. With that, Julia, I'd be happy to take any questions or have any discussion.
Okay, we have time for just a few questions. And if there's a lot of discussion, I think we can, cover the C business and come back to questions if you can stay for an extra 5 or 10 minutes.
Fair enough.
There was just one thing in the chat so far, which said, congrats, excellent presentation. So feel free to either chat your question or unmute. It's hard for me to see everybody to call on somebody. So, Steve, I did have a question. With the Agile high velocity development process that you developed, how was that integrated with the data? What effect did it have on the stuff that, your everything that you just talked about?
So integrating the Agile methods for us really meant doing things a lot more iteratively, and instead of the big bang, committing to something that's 6 months out, 12 months out, giant design phases, giant development phases, traditional waterfall. It really meant doing things a lot more iteratively and doing things a lot more incrementally. But and that, whether that's, gathering requirements and using user stories and all those sorts of things. But what didn't change for us is the fact that we wanted to use those kind of those types of iterative, responsive practices that, customers like so much. We still wanted to use data. So we still track our time, we still measure sizes of things. So instead of, traditional planning poker where, we might just choose somewhat arbitrary t-shirt sizes or Fibonacci sequences, we actually measure the sizes of those things to help us do that empirically. So it was really more about applying the metrics that we were already using and doing that in a much more iterative, responsive way.
Thank you. Carlos has a link in the chat for a similar study in the industry level. So, go to this chat if you'd like to get that link. Brad, go ahead. We have time for a question and a comment.
All right. Hey, Steve, could you go back to slide 9? I love the fact that you brought up the idea of I wouldn't say hedging your bets, but when schedule is critical, having a value somewhere between the normal number and the upper projected limit, that's a phenomenal way to mitigate risk. I love that. And you followed up on later by talking about the 90%. But this is a great way to say, hey, look, we're really critical on schedule here, so we do not want to say, well, half the time will be good. And this is really nice. I appreciate that. I had a question on slide 8. Excuse me. So slide 8, normally we have a big cloud in the lower left, like 0 to 10, it's just a shotgun. And I didn't see it here. And I was wondering if you guys weeded that out or just looked at numbers that were bigger than an estimate, bigger than a certain amount.
That's a good question. No, I don't think this is data that's been weeded out. These are the, I believe, the full population of components that are relevant to at least a team over a certain period of time. It may have, we may have removed data points that were from, this is a very long running project for us, so it may not include data points that are from like 5-10 years ago. But these are data points that are relevant to the existing team, and it's the full population. Yeah.
Okay.
And just for the benefit of everybody, typically, if there's 2 types of estimation errors, you either misestimate, a component you have, or you forget that you need a component. And when you have 0 estimated hours and then actual time, those are all the ones where you forgot you needed something. So there are 2 different types of errors you can make in estimating. So you guys are really, at least you remember everything you have.
Well, no, I don't think that would be necessarily a proper a proper interpretation. If we didn't have an estimate, like if there was an unplanned component that could have been there for various reasons, I don't think that would get plotted here. It would get plotted, maybe it would get covered, not the component level regression, which this is showing, but it would be covered by some of the either activity level or even project level regression that we sometimes apply.
Okay.